In this video, we will discuss infinite limit and also vertical asymptote of a given function, right? Let's see a motivating example for the infinite limit. Let's see that, right? So let's see, we have a function here, example. Our function here, formula is f of x equal to 1 over x squared, or sometimes we write this as x to the power -2, right? Same thing. We know that the domain of such a function is everything but the numbers which make the denominator to be 0, right? So this is basically from -infinity to 0, union from 0 to positive infinity, right? So that's one way to represent it. Another way for sure is you can write this as all possible real numbers, but cannot be 0. If you plug in 0, you get 1 over 0. So f of 0 is undefined. So we are looking for all the numbers which make f of x well-defined. That is the domain of a function. Now, okay, we wonder what happens at 0, right? So if you try to list a few numbers, so x, and make the x value here getting closer and closer to 0. So this is f of x, which is 1 over x squared, right? And because it's for sure is symmetric, because square will make positive or negative to be positive, right? Let's start from 1 here. So this will be 1. 0.1 here, because we make it closer and closer to 0. This will give you a 100. If you get 0.01, this will give you 10,000. Now you can keep making the x value closer and closer to 0. Let's if you want to do, you can do one more, which is 0.001. You get 1 followed by 60, right? A million. And the same thing for negative numbers, because as I mentioned, the square will make all the negative number to positive numbers. You can see that the y value is getting larger and larger if you try to imagine that no upper bound, right? We say this happens, if this happens, we say the function value goes to positive infinity. So if you try to write down a notation for that, the reasonable way to do that is the limit of this function at 0 as x goes to 0. The function value for sure doesn't exist. And this is positive infinity. So positive infinity is never a number. Just representing some values getting larger and larger without upper bound, which means go to infinity. Right? If you try to confirm it, look at the graph, right? The graph of this function looks like this. So this is our x, y. If you try to sketch the graph of this function, it's getting closer and closer to the y-axis, right? As x goes 0 on the right side, and same thing happens as x goes 0 on the left side. They are symmetric about y-axis. In this case, we know that our curve is getting closer and closer to a line. This line here is called asymptote, right? So this x equal to 0, which is our y-axis, is asymptote. And because this is vertical, we call that vertical asymptote. So vertical asymptote at a number, which is 0 in our case, the limit of the function goes to infinity on one side or both sides, right? Or sometimes negative infinity, which means go larger and larger negatively without lower bound. So that's the meaning of that. Okay. Now let's see the official definition for the infinite limit, and we will see example, right? So definition here. Let me try to move the page a little bit. Definition here. So we are assuming the function is defined around a number a, right? F of a may not exist, but when x is near a, f of x is well defined. Then we define this, right? We say that our function value as x goes to a here, go to positive infinity, right? Very, very similarly, you can define the function go to negative infinity, right? So if the values of f of x can be made arbitrarily large. Right? Always you make your function value large or getting closer and closer to something by what? Restricting your x, right? By taking x sufficiently, right? Sufficiently close to a. One very important thing here is x cannot be a, right? Because f of a may not exist, but not equal to a. So that's the definition for a function goes to infinity at a number, right? And very similarly, you can define other definitions. For example, as x goes to a, f of x is negative infinity, or as x goes to a on the right side, f of x goes to positive infinity or negative infinity, right? Or the last group as x goes to a on the left side, f of x is positive infinity or negative infinity, right? So that's two definition combine the left or right limit by the right hand limit or left hand limit with positive or negative infinity, you get a bunch of new definitions, right? Let's see a quick example here. Let's see a very quick example. Right? So we want to know the limit as x goes to 3 on the right side, 2x over x minus 3, right? What's this? Right, you can see that the denominator goes to 0 because x is getting closer and closer to 3, then x minus 3 will get closer and closer to 0. So let's try to write down a list a few numbers, right? So let's x here and 2x over x minus 3, right? I try to see what happens. If you have this is, let's say 3.1, you get 2.3 times, 2 times 3.1 over 0.1, right? Which is about 62, right? If you try to 0.01, you try to do that 2.3.01 2 times over 0.01, right? You can see this is getting bigger, right? This will be 600 something, right? If you try it one more time, this is 3.001. This will be 2 times 3.001 over 0.001, right? Now you can see that this is getting larger and larger. Imagine that this for sure goes to infinity, right? If you try to analyze it in a more algebra way, you can see that as what? As x goes to 3 on the right side, and 2x goes to, that's easy, go look at numerator, 2x go to 6, right? X minus 3 go to 0. But because x goes 0, go to 3 on the right side, which means x is always greater than 3, right? So x goes 0 on the right, positive 0, which means x is getting closer and closer to x minus 3 is getting closer and closer to 0 on the right side, right? So you have everything is positive. So 2x over x minus 3 is getting larger and larger, positively unbounded. So this is positive infinity. So this is positive infinity. So that's how do we decide this infinite limit is positive or negative, right? So very similarly, this is our example 1 here. Very similarly, you can try to analyze as x go to 3 on the left side, 2x minus x minus 3. This one actually goes to negative infinity because this one is basically goes to 6 over 0 minus. So one negative thing give you the sign of the limit is negative infinity, right? So now let's try to write down the definition of vertical asymptote definition. So x equal to a, clearly x equal to some number is a vertical line, right? So is a vertical asymptote of y equal to f of x, that's our function, if one of the following holds, right? They're up because as long as x, the curve is getting closer and closer to the line, this is called asymptote, vertical asymptote. There are many ways, right? 6 ways actually, right? And the first one here is for sure as x goes to a, f of x is infinity. And second one here is as x goes to a, f of x is negative infinity, right? And third one here will be what? As x goes to a on the right side, the function, yeah, approaching the vertical line on one side. And from the top, which means infinity, and the fourth one will be as x goes to a on the right side, f of x is negative infinity. And number 4 here, number 5 is as x goes to a on the left side. Let me erase this left side, which means this is a minus f of x is negative infinity, or number 6, which is as x goes to a on the left side, f of x, wait, this is positive infinity, the last one is negative infinity, right? So it's just a 6. If either one of this happens, this is a vertical asymptote. You can see that by our discussion above. A good example by our calculation here. Suppose this is our function here. That's our number, right? So this two equation says x equal to 3 is a vertical asymptote asymptote of the function here is f of x equal to 2x over x minus 3, right? So that's basically how do we get the vertical asymptote. You can see that vertical asymptote happens at the number, could happen at the number which make the denominator to be 0, right? If that happens, that number could be a vertical asymptote, but sometimes may not be, right? We'll see examples later.